Imagine the silence of space, a darkness that stretches in every direction without end. It seems empty, but the emptiness is an illusion. Within it float the true engines of the cosmos, the stars. From a distance they appear as simple points of light, scattered like glitter across black velvet. But if you step closer in thought, if you dive inward past the glare and into the hidden heart of a star, you find a battle raging that has lasted for billions of years. This battle is not fought with weapons or armies. It is fought with the most fundamental forces in the universe. Gravity pulls inward, crushing matter toward the center. Fusion pushes outward, the fire of creation, born from atoms, slamming together with unimaginable force. Every star you see is suspended in this delicate balance, a balance so precise that the fate of worlds depends on its endurance. Gravity is always the aggressor. It never tires, never weakens, and never negotiates. It is the same gravity that keeps you bound to the earth, the same pull that keeps planets circling the sun, but inside a star, it is magnified into a colossal pressure. If nothing resists it, gravity will crush matter into smaller and smaller volumes, driving temperatures and densities higher than anything we can truly imagine. But fusion stands in the way. When hydrogen, the simplest and most abundant element, is forced close enough together, its nuclei merge. In that moment of union, a fraction of the mass vanishes and is transformed into pure energy. That energy pushes outward with the fury of light and heat, creating a counterforce that holds gravity at bay. This is why stars shine. Every beam of sunlight warming your face is the evidence of this eternal struggle. Photons released from nuclear battles deep in the solar core. The sunlight we see today was born in reactions that began millions of years ago, trapped inside the star as it scattered, absorbed, and re-emitted its way to freedom. By the time it escapes into space, the outward pressure of all those photons pushing against the weight of the star keeps the collapse in check. Gravity wants to win instantly. Fusion prolongs the fight, buying time in spans so vast that the human mind can barely hold them. Yet even as fusion holds the line, there is a ticking clock hidden within the fire. Fusion depends on fuel. A star has only so much hydrogen in its core, and with every passing second, billions upon billions of atoms are being fused into helium. Over eons, the balance shifts. The star grows older, and the hydrogen grows scarcer. What once was an effortless standoff becomes a contest with diminishing reserves. Like a candle burning itself toward the end of its wick, the brilliance of the star hides a slow countdown toward exhaustion. To see this more clearly, picture our own Sunday. It is a middle-aged star, about 4.5 billion years into its life. At its core, gravity squeezes hydrogen into helium at a rate so immense that the star loses about 4 million tons of mass every second. Those tons are not destroyed, but converted into energy, streaming outward as light and heat. This sounds catastrophic, but the sun is so massive that even at this rate, it can continue burning for another 5 billion years. To us, that sounds eternal. To the cosmos, it is only a moment. The balance is fragile. If gravity were stronger by just a fraction, stars would collapse before fusion could even begin, and the universe would be dark and cold. If fusion were more efficient by just a fraction, stars would explode outward the moment they lit, dispersing matter without ever forming stable worlds. But the constants of physics allow a perfect equilibrium. This narrow balance is why galaxies glow, why planets form, why life has a chance to exist. The war inside a star is not only a spectacle of nature, it is the reason for everything we know. Still, every battle must end. The outward push of fusion cannot last forever. Hydrogen runs low, helium accumulates, and the star begins to change. The core contracts, temperatures rise, and fusion of heavier elements begins in pulses of violence and renewal. The outer layers swell and shift, the star becomes a red giant, and gravity presses ever harder on what remains within. Even then, fusion can only delay the inevitable. Sooner or later, the balance fails. When that moment comes, gravity will no longer have an opponent. It will not rush in with sound or spectacle, because space is silent, but the effect will be cataclysmic. The very matter of the star will begin to collapse inward. If the star is light enough, the collapse halts with one final stand of physics. If the star is heavy enough, gravity will not be stopped at all. What follows is death on a stellar scale. a death that can echo across galaxies. The clock keeps ticking, and when the last second of fuel is spent, gravity claims its prize. The heart of a star is not a tranquil place, though from the outside it glows with calm brilliance. Deep inside, particles are locked in relentless collision. Imagine the density, atoms packed so tightly that each square centimeter contains more material than mountains compressed into grains of sand. In this furnace, temperatures soar to millions of degrees Celsius, so high that electrons cannot cling to their nuclei. What remains is a plasma, a sea of free protons and electrons rushing with such energy that they overcome their natural repulsion and slam together. When they fuse, hydrogen becomes helium, and with each reaction, the star roars a little brighter, though to our eyes, it appears steady and unchanging. But fusion is not simple. It occurs in chains, each step depending on chance collisions. The most common pathway in stars like our Sun is the proton-proton chain, where protons join to form heavier isotopes and eventually create helium. At each stage, a little energy escapes as light or as ghostly neutrinos that rush through the star and out into space. These neutrinos pass through matter almost without interaction. Even now, billions of them are streaming through your body every second, messengers from the core of the Sun, silent evidence of the war beneath its surface. It is easy to think of stars as eternal because human lives are so short by comparison. Our entire recorded history is less than a blink in the life of the Sunday, yet when measured against the lifespan of the cosmos itself, stars are temporary fires, burning brightly for a time before fading. The delicate balance of gravity and fusion allows them to live for billions of years, but it is a balance doomed to fail. This inevitability shapes everything, because without endings there can be no beginnings. As hydrogen depletes in the core, the outward pressure weakens. Gravity, patient and relentless, senses the faltering of its rival. The core begins to contract. The contraction raises the temperature, and for a while this allows fusion to continue with new elements. Helium, once only a byproduct, now becomes fuel. Helium nuclei fuse into carbon and oxygen, heavier building blocks of matter. But this new form of fusion requires even higher temperatures, and the cycles are shorter. The star begins to change visibly, swelling and reddening, shedding layers in the process. To an observer, it becomes a red giant, bloated and luminous, beautiful yet unstable. Our own Sun will one day swell into such a giant. It will expand so far that it will consume Mercury and Venus, and Earth itself may be scorched or swallowed. Long before that, the oceans will boil away, and the atmosphere will be stripped, leaving a barren rock. Life as we know it cannot survive such transformation. Yet this destruction is not random cruelty. It is the natural outcome of the eternal struggle, the moment when fusion falters and gravity presses its advantage. The Sun is an ordinary star, neither too small nor too large. In its old age, it will not collapse into something exotic like a neutron star or black hole. Instead, when helium is gone, the core will shrink into a dense ember, known as a white dwarf. Its outer layers will drift away into space, forming a planetary nebula, glowing shells that will fade over tens of thousands of years. The white dwarf, supported by a strange form of pressure from the quantum behavior of electrons, will remain for billions of years, slowly cooling until it is dark. This is the quiet death awaiting ordinary stars. But stars more massive than the Sun face a harsher fate. For them, gravity is far stronger, and their cores burn hotter. They exhaust their fuel faster, living shorter but more violent lives. Their struggle with gravity ends not in quiet fading but in violent collapse, in explosions so powerful that they can outshine entire galaxies. These are supernovae, the spectacular deaths of massive stars. In them, gravity finally wins its long contest, crushing the core so completely that new and extreme objects are born. Even as we describe these destinies, it is important to remember the role such deaths play in the universe. The elements forged in stars, released in their deaths, become the raw material for planets, for oceans, for life itself. Without the slow-ticking clock of stellar fuel and the collapse that follows, there would be no carbon in our bodies, no oxygen to breathe, no iron in our blood. The stars are not eternal, and we should be grateful for that. Their struggle gives meaning to the matter around us. At the end of this balance, when fusion is no longer enough, when the clock strikes its final moment, gravity steps forward and takes full command. This transition marks the true beginning of stellar collapse, a process that will lead to some of the most extraordinary phenomena in nature. The first step is quiet, the gentle cooling of small stars. But for giants, the stage is set for collapse on a scale that shakes the fabric of space itself. The struggle within a star is invisible to the eye, yet it defines the light that reaches across space. If you were to float near the surface of the sun, shielded somehow from its searing brilliance, the light would appear steady, unwavering, almost eternal. But beneath that surface, the balance between gravity and fusion is always shifting, always adjusting to the tiniest changes in pressure and temperature. A star is not static. It breathes in slow cycles, its heart beating in nuclear rhythms. The outward pressure of fusion grows stronger or weaker depending on the available fuel, and gravity responds instantly, pressing harder when the flame flickers, relaxing slightly when fusion blazes. This constant adjustment is why stars can survive for billions of years, yet no adjustment can last forever. The fuel that powers fusion is finite. Even in a star as vast as the Sun, the number of hydrogen atoms available is limited. With every passing second, countless of them vanish into helium, converted into the light that sustains Earth and every living thing upon it. Imagine an hourglass where each grain of sand is an atom of hydrogen. The sand seems endless, but the stream is steady. Grain by grain, the supply diminishes. The star does not know it is running out of time, but the clock moves forward all the same. As the supply dwindles, the heart of the star changes. Hydrogen fusion can no longer fully oppose gravity, and the core contracts. Temperatures rise, and new pathways of fusion open, first with helium, then with carbon, oxygen, neon, and beyond. For massive stars, the sequence continues until iron is formed. But iron is the limit because it cannot yield energy through fusion. It represents the dead end of nuclear fire. Once iron dominates the core, gravity finally achieves its long-awaited victory. In less massive stars, like our Sun, the chain halts much earlier. The Sun will never reach the point of forging iron in its core. Instead, it will expand, shed its outer layers, and settle into the quiet life of a white dwarf. Gravity will press inward, and electrons, through their quantum resistance, will push back. The result is an object no larger than Earth but with a mass nearly half that of the Sunday. This is not a defeat for gravity so much as a stalemate, a compromise enforced by the laws of physics. The star will fade, but it will not be crushed beyond recognition. For massive stars, however, gravity's assault is relentless. These stars live fast and die young, some surviving only a few million years before collapse begins. Their final act is not gentle but catastrophic, a collapse so sudden that the outer layers rebound outward in a titanic blast. This is a supernova, a moment when a single star can outshine all the others in a galaxy. What remains behind depends on the mass of the core. If it is small enough, the collapse halts with neutrons packed together in impossible density, forming a neutron star. If the core is greater still, nothing can stop gravity. The collapse continues until even light cannot escape, and a black hole is born. We see stars as twinkling points in the night sky, eternal to our brief lives. But each of them carries this destiny. The balance of gravity and fusion is always temporary. It is only a matter of when, not if, gravity will reclaim the matter it has allowed to burn. This truth is sobering, yet it is also wondrous. Because without this cycle of struggle and collapse, the universe would be sterile and lifeless. The death of stars seeds space with the elements of life, reshapes galaxies, and creates the most mysterious objects known. So as we look upward, we are not just seeing lights in the sky, we are seeing battles already half decided, destinies already written in physics. The light of the sun will last for billions more years, but one day, it too will falter. On that day, the balance will end, and gravity will emerge the victor. This is the law of the cosmos. It is the promise written in the heart of every star, a promise that the struggle cannot last forever. The end of balance is the beginning of collapse. What follows is not only death but transformation. For stars like the sun, the transformation is gentle. For others, it is violent beyond imagining. In the next part of the story, we will follow these endings more closely. We will see how ordinary stars, the most common kind in the galaxy, live out their last days and fade into remnants. And then, we will turn to the giants, where collapse is not gentle at all, but apocalyptic. The struggle inside a star is only the beginning of a tale that stretches from light to darkness, from creation to destruction, and back again. Not every star dies in violence. Some slip quietly into darkness, their end a slow fading rather than an explosion. These are the ordinary stars, the small and middle-sized suns scattered across the galaxy in their billions. They burn more modestly than their massive cousins, living long lives that stretch into the tens or even hundreds of billions of years. Their deaths are not marked by shattering blasts, but by a graceful unraveling, as if the universe itself whispers them to sleep. Yet even in this quiet passing, gravity remains the executioner, and what follows is as strange and beautiful as any cosmic event. Picture a star not so different from our Sunday. For billions of years it has kept the balance, gravity pressing inward, fusion pushing outward, the struggle holding steady. But as hydrogen dwindles, the balance begins to tilt, the outward force weakens, the core contracts, and the temperature rises. Around this shrinking heart, a shell of hydrogen still burns furiously, pouring energy into the outer layers. The star swells, its surface cools, shifting from white to red, and it becomes a red giant. To distant worlds, it appears as if the star has grown old and bloated, a swollen ember filling its sky with crimson light. For the star itself, this is the final act of fusion. The helium that gathers in the core eventually ignites in bursts, fusing into carbon and oxygen. But for a star with the mass of our Sun, the fire can go no further. The core cannot reach the temperatures required to fuse heavier elements. When the helium is spent, no new fuel remains. The core contracts again, and the outer layers grow unstable. Slowly, like a veil drifting from a dancer's hand, the star releases its outer layers into space. Clouds of gas expand outward, glowing in eerie colors from the radiation of the dying core. This is a planetary nebula, a misnamed phenomenon that has nothing to do with planets, but everything to do with stellar death. Seen through telescopes, planetary nebulae are some of the most exquisite sights in the heavens. Delicate shells of blue, green, and crimson floating like cosmic lanterns. What remains at the center is tiny but dense, a white dwarf. Imagine a sphere no larger than Earth, yet containing half the mass of the Sunday. Its gravity is immense, its surface scorching hot, glowing with the energy of a star's last breath. But no fusion sustains it. Instead, it is held up by electron degeneracy pressure, a quantum rule that forbids electrons from occupying the same state. This strange law of physics prevents gravity from crushing the star further. The white dwarf shines for billions of years, gradually cooling until it becomes invisible, a black dwarf lost in the dark. For stars even smaller than the Sun, the story is quieter still. Red dwarfs, the most common stars in the galaxy, burn hydrogen so slowly that none have yet died in the entire history of the universe. One day, trillions of years from now, when all such stars have finally consumed their fuel, they too will fade into white dwarfs and then into darkness. These will be the last lights to go out, the final embers of a dying cosmos. Even in their silence, the deaths of ordinary stars matter. The shells they shed enrich the space around them with carbon, oxygen, nitrogen, and other elements. These drifting clouds of gas can later collapse to form new stars and new planets. Our own solar system is built from the ashes of earlier generations of such stars. Every breath of air, every drop of water, every cell in our bodies contains atoms once forged in the hearts of long-dead suns. Their quiet passing is the foundation of life itself. Yet ordinary stars, for all their importance, represent only one kind of ending. Their deaths are steady, predictable, and serene. But in the cosmos, not all stars are so merciful. There are stars far heavier, stars that live fast and die violently. For them, the struggle against gravity ends not in quiet surrender, but in catastrophic collapse. And it is to those stars that we must turn next, to witness the most dramatic deaths in the universe. The transformation from star to red giant is among the most dramatic changes a celestial body can endure. Imagine a sun like ours, steady and golden for billions of years, suddenly swelling until it is hundreds of times larger. The surface cools as it expands, shifting from yellow to a deep, ruddy glow. From a nearby world, the sky would be consumed by this swollen giant, its light crimson and unrelenting. Oceans would boil, mountains would melt, and entire planets could be swallowed whole. Yet from far away, the spectacle is breathtaking. The star shines brighter than ever, a beacon of impermanence in the dark. Inside, the story is one of desperation. Hydrogen fusion continues, but now it burns only in a shell surrounding the contracting core. The core itself, packed with helium, grows hotter and denser. At a certain threshold, helium ignites in what astronomers call the helium flash, a sudden onset of fusion that converts helium into carbon and oxygen. The star stabilizes briefly, shrinking slightly as the new fuel takes hold. But this reprieve is temporary. Helium fusion is less efficient than hydrogen fusion, and it runs its course in a fraction of the time. The countdown accelerates. As the core contracts again, the outer layers drift farther away, loosely bound by gravity. Radiation pressure pushes them outward, sculpting them into expanding shells. From Earth, we have captured these shells through telescopes, and the images reveal the artistry of physics. Some resemble delicate rings, others butterfly wings, still others ghostly spheres glowing against the void. They are planetary nebulae, the final breath of dying stars. Their colors are not illusions. Oxygen glows green, hydrogen shines red, and nitrogen burns blue. These hues tell the story of chemistry, a story that connects the death of stars to the birth of planets. In the center of these nebulae lies the white dwarf, impossibly dense, a monument to what remains when fusion is done. The physics of its support is unlike anything in our daily lives. Electrons, bound by the rules of quantum mechanics, resist being squeezed into the same place. This resistance is not strength in the traditional sense. It is a rule of nature, a law that cannot be broken. And so the white dwarf stands, gravity pressing inward with unimaginable force, electrons holding their ground. The result is an object with the mass of the sun and the volume of the Earth. A teaspoon of white dwarf matter would weigh as much as a mountain. Over time, the white dwarf cools. Its brilliant glow fades, first to a dull ember, then to invisible heat, and eventually to nothing at all. It becomes a black dwarf, a remnant colder than space, indistinguishable from the void around it. No black dwarfs exist yet, because the universe itself is not old enough. But in the far future, when trillions of years have passed, they will drift silently through space, the fossils of ancient stars. Stars smaller than our sun take an even slower path. Red dwarfs, which make up the majority of stars in our galaxy, are miserly with their fuel. They burn hydrogen so efficiently that they can last for trillions of years. None have yet reached the end of their lives, because the universe is only about 13.5 billion years old. But eventually, they too will expand, shed their outer layers, and become white dwarfs. In the very distant future, when all the brighter stars have died, these faint red embers will be the last beacons of light in the cosmos. It is tempting to see this as a bleak outcome, a universe fading into darkness. But consider what these ordinary deaths achieve. Each planetary nebula, each drifting cloud of expelled matter, enriches the interstellar medium with heavier elements. Without this enrichment, the next generation of stars would be pure hydrogen and helium, lifeless gas, with no potential for planets or biology. Instead, carbon, oxygen, nitrogen, silicon, and countless other elements circulate through space. They are gathered by gravity into new systems, new planets, and eventually new life. The death of ordinary stars is the seedbed of creation. The Earth itself is proof of this cycle. The iron in our blood, the calcium in our bones, the carbon in every cell, all were forged in stars that lived and died long before the sun was born. Those stars did not explode in cataclysm. They faded into nebulae, scattered their ashes into space, and left behind white dwarfs that still drift silently today. Our existence is their legacy, written into every breath and heartbeat. The quiet death of ordinary stars is not an ending to mourn, but a beginning to celebrate. And yet, as gentle as these endings may seem, they are not the whole story. For in the cosmos, some stars are giants, far more massive than our sun, with fates far more violent. For them, the balance does not end in quiet surrender. It ends in collapse, so sudden, so furious, that the very fabric of space quakes. To understand the true power of gravity, we must leave behind these ordinary deaths and turn our gaze toward those greater giants, where endings are written in fire. The image of a white dwarf glowing at the heart of a planetary nebula is haunting. It is the last ember of a once brilliant star, the skeletal remains of a life that spanned billions of years. If you could approach such a remnant, the experience would be surreal. The object before you would be small, no larger than Earth, but its mass would pull at you with irresistible strength. The surface gravity would be hundreds of thousands of times greater than what you feel on Earth. A single step would crush you instantly, your body compressed by forces beyond comprehension. And yet, despite this unimaginable intensity, the white dwarf is stable. It no longer changes, no longer burns. It simply glows, slowly radiating away its stored heat, until one day, countless eons from now, it becomes invisible. This is the destiny of ordinary stars. It may seem uneventful compared to the titanic violence of supernovae, but there is a quiet grandeur to it. The planetary nebula that surrounds the fading star drifts outward over thousands of years, mixing with the interstellar medium. Eventually, these gases join the galactic clouds, from which new stars are born. The cycle is complete. Matter collapses, shines, expands, and collapses again, a rhythm that echoes across cosmic time. Without this steady recycling, galaxies would be sterile deserts of hydrogen. With it, they are rich tapestries of chemistry, capable of producing the complexity that we call life. The importance of these ordinary deaths cannot be overstated. Consider the carbon atom in your body. It was forged in the last burning stages of a red giant, fused from helium, under crushing pressure and searing heat. When the star shed its layers, that carbon was carried into space, drifting for untold millions of years, until it found itself caught in a new cloud of collapsing gas. That cloud gave birth to the sun, the earth, and eventually to you. In this way, the deaths of ordinary stars are not ends at all, but beginnings written on cosmic scales. Still, there is a melancholy to these fates. White dwarfs, for all their strangeness, are dead stars. They shine only with residual heat, not with the fire of fusion. Over billions and trillions of years, they cool and fade. When the universe is old beyond reckoning, it will be filled with these corpses, black dwarfs, invisible in the darkness. Even then, gravity will still hold them, silent reminders of what once burned. And what of the smallest stars, those red dwarfs still burning today? Their patience is unmatched. They sip their fuel slowly, so slowly that the universe has not yet witnessed even one of their deaths. When their time does come, they too will swell and fade into white dwarfs. But this will not happen for trillions of years. If humanity were to last that long, we would see the last lights flicker out in skies filled only with faint red embers. The universe would grow colder and darker, lit only by the rare flares of massive stars that still collapse violently. The deaths of ordinary stars are a lesson in scale. To us, they seem eternal. To the cosmos, they are fleeting. They remind us that even stability is temporary, and that change is the only constant written into the laws of physics. But they also remind us that endings need not be violent to be profound. The gentle unraveling of a star, the quiet formation of a white dwarf, the soft glow of a planetary nebula, these are as much a part of the universe's story as the grandest explosions. Yet the universe is not content with silence alone. For every quiet passing, there is a death written in fury. The most massive stars, those that burn their fuel in mere millions of years, do not fade gently. When their cores are filled with iron, when fusion can no longer oppose gravity, collapse comes with stunning speed. The star's heart implodes in less than a second, and what follows is an explosion so bright it can be seen across galaxies. These are supernovae, the ultimate revelation of gravity's victory. And so we move forward. We have seen how ordinary stars live and die, how they leave behind remnants that endure for ages, how their gentle deaths enrich the galaxy with the ingredients of life. But now we must confront the other path, the path of the giants. Their deaths are not quiet, they are cataclysmic, reshaping everything around them. In the next chapter, we will witness collapse not as a whisper, but as a roar, the violent end of massive stars, and the birth of extraordinary objects. There are stars whose lives burn brighter and faster than our sun could ever dream. These are the giants of the galaxy, immense furnaces tens of times more massive than the sun, their cores seething at temperatures so high that they blaze through their fuel with reckless speed. Where the sun will live for 10 billion years, these giants may survive for only a few million. Their brilliance is spectacular, but it comes at a cost. They are destined not for gentle fading, but for cataclysm. When their fuel runs out, they do not slip into silence. They collapse, and in that collapse, they unleash some of the most violent events in the universe. The reason lies in the chemistry of fusion. A star lives by converting lighter elements into heavier ones, releasing energy in the process. Hydrogen fuses into helium, helium into carbon and oxygen, carbon into neon and magnesium, oxygen into silicon, and finally silicon into iron. Each step releases energy. Each step fights back against the inward crush of gravity. But iron is different. When nuclei of iron fuse, they do not release energy. Instead, they consume it. The star has reached a dead end. Iron is the ash of nuclear fire, the element that signals the end of fusion's resistance. Inside a massive star, the buildup of iron is inevitable. Over time, its core fills with iron, while the outer layers continue to burn in shells, each one fusing a different element. The structure resembles an onion, with hydrogen at the surface, helium beneath, then carbon, oxygen, silicon, and finally iron at the heart. This layered core is unstable, and it cannot last. Gravity presses ever harder on the iron heart, while fusion in the shells above provides only temporary relief. The star is living on borrowed time. When the core reaches a critical mass, the balance is broken. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. This process, called electron capture, removes the pressure that once held up the star. In less than a single second, the iron core collapses. Imagine a sphere the size of Earth shrinking to a ball only a few kilometers across in the blink of an eye. Matter falls inward at a significant fraction of the speed of light. Densities rise to unimaginable levels, and gravity's triumph is complete. The outer layers of the star, still falling inward, suddenly encounter the rigid neutron core that has formed in the collapse. The infalling matter rebounds, sending a shockwave racing outward. This alone would not be enough to tear the star apart, but the neutrinos released during collapse add their energy, reviving the shockwave and driving it to catastrophic strength. In a moment, the star explodes in a supernova, blasting its outer layers into space at thousands of kilometers per second. The violence of such an event defies comprehension. For a brief time, a single supernova can outshine an entire galaxy of billions of stars. The energy released in those seconds exceeds what the sun will emit in its entire 10 billion-year lifespan. Light and radiation pour into the cosmos, while heavy elements forged in the chaos are scattered across interstellar space. What began as collapse becomes creation, a paradox written into the heart of physics. To distant observers, the explosion is a beacon. Ancient civilizations on Earth once saw such lights in the sky, new stars appearing suddenly where none had been before. Today, with telescopes, we study them in detail, watching the shells expand, measuring the spectra of the elements hurled outward. Each observation confirms what theory predicts, that gravity, in winning its struggle, creates the very ingredients of planets, oceans, and life. Yet the story does not end with the explosion. At the heart of the wreckage, something new remains. If the collapsing core is small enough, it stabilizes as a neutron star, an object of almost inconceivable density. If the core is larger still, nothing can stop gravity. It continues to collapse past the neutron stage, creating a black hole, a tear in space-time from which not even light can escape. These are the legacies of massive stars, born not in peace, but in fury. The collapse of a massive star is sudden, violent, and final. For millions of years, the star has fought its battle, burning one element after another, fusing hydrogen into helium, helium into carbon, carbon into heavier and heavier elements, each stage faster than the one before. What takes billions of years in an ordinary star can take only a few million in a giant. The larger the mass, the shorter the life. It is as if these stars live in a frenzy, racing toward their destruction. At the end of this race lies iron, the element that spells doom. Fusion in the core no longer releases energy, and without energy, there is no outward pressure to resist gravity. In an instant, the core begins to implode. Matter that once formed the very heart of the star collapses inward at speeds beyond imagining. Atoms are crushed, electrons forced into protons, creating neutrons and releasing an unstoppable torrent of neutrinos. The collapse happens so quickly that the outer layers of the star have no time to react. They continue to fall inward, rushing toward the core like an ocean pouring into a bottomless hole. Then comes the rebound. The core, now a ball of neutrons packed tighter than the nucleus of an atom, halts the collapse with the last possible resistance of physics. The infalling layers slam into this core and ricochet outward, sending a shockwave racing through the star. Alone, the shockwave would stall, suffocated by the immense weight of the material still falling inward. But the flood of neutrinos released during the collapse transfers a fraction of their vast energy to the surrounding matter, reviving the shock and turning it into an explosion. the star tears itself apart from the inside, blasting its outer layers into space with unimaginable force. What follows is a supernova, an event so bright that it can outshine the combined light of billions of stars in its host galaxy. The energy released in a few seconds surpasses the energy the sun will radiate in its entire 10 billion-year lifetime. Light and radiation flood the cosmos, reaching across thousands or millions of light years. To ancient eyes on Earth, such explosions appeared as new stars, suddenly brighter than all others, visible even in the daytime sky. Today, with telescopes, we can trace their expanding shells, observe their glowing remnants, and measure the fingerprints of the elements created in their fury. The violence is not mere destruction. In the extreme heat and pressure of the explosion, new elements are forged. Gold, uranium, and countless other heavy atoms are born in these moments, scattered across space to enrich the galaxy. Without supernovae, the periodic table would end with iron. The universe would be a simpler place, devoid of the materials needed for planets and life. It is in the collapse of massive stars that nature reveals her most creative violence. At the very center, hidden within the expanding debris, lies the remnant of the collapse. Sometimes it is a neutron star, an object so dense that a teaspoon of its matter would weigh billions of tons. Sometimes it is something darker, a black hole, where gravity has triumphed so completely that not even light can escape. The difference depends on mass. If the collapsed core is below a certain limit, neutron pressure halts the fall. If it is above that threshold, gravity has no opposition, and collapse continues forever. The aftermath of a supernova reshapes its surroundings. Shockwaves sweep through the interstellar medium, compressing clouds of gas and triggering the birth of new stars. The material cast into space becomes part of new systems, new worlds, new possibilities for life. Collapse and explosion are not the end, but the beginning of cycles far larger than any single star. The death of a massive star is an event that echoes through time, shaping galaxies and seeding the cosmos with the ingredients of existence. And yet, even with all our science, the exact details of how the shockwave revives, how neutrinos transfer their energy, and how collapse stabilizes remain among the deepest mysteries in astrophysics. What we know is that the process works. We see the remnants, we measure the light, and we trace the elements in our own bodies back to these deaths. The universe itself confirms the story, written in atoms and starlight. When a massive star collapses, time itself seems to fracture. The core implodes in less than a second. The shock wave forms in another heartbeat, and the explosion blossoms across space in the blink of an eye. Yet the consequences stretch for millions of years. To watch such an event unfold with human senses would be impossible. But if we could slow the clock, we would see a sequence, both terrifying and magnificent. First, the surface of the star trembles, then brightens as the shockwave races outward. In moments, the outer layers are torn away and hurled into space at thousands of kilometers per second. The star that has burned for millions of years is gone, replaced by a cloud of incandescent debris, spreading ever wider. In the heart of the explosion, matter has been transformed. The iron that marked the end of fusion is smashed by the fury of collapse and rebound, its nuclei shattered and reassembled into new elements. In these brief seconds, the universe forges gold, platinum, uranium, and many other heavy atoms that fusion alone could never create. These atoms stream outward, carried by the blast, destined to drift in interstellar space, until gravity gathers them into new worlds. When you hold a gold ring or breathe oxygen, you are touching the memory of ancient stars that collapsed long before the sun was born. The light from a supernova can travel across galaxies. Some explosions have been so bright that they were visible from Earth in broad daylight, recorded by ancient observers who did not know they were witnessing the death of a distant Sunday. Today, astronomers detect the afterglows with powerful telescopes, mapping the expanding shells of gas and dust. These glowing remnants, such as the Crab Nebula, are vast testaments to the power of collapse, beautiful structures of chaos, frozen in motion as they spread through the galaxy. Yet the explosion is not the end of the story. At the center of the wreckage remains the collapsed core, an object unlike anything else in the universe. If the mass is small enough, the collapse halts when neutrons themselves resist further compression. The result is a neutron star, a body so dense that mountains would be crushed flat in an instant, and so compact that it spins like a cosmic top, beaming radiation across the galaxy. If the mass is greater, even neutrons cannot resist, and gravity wins utterly. The star collapses into a black hole, a place where space and time themselves are bent beyond recognition. Supernovae are both destroyers and creators. They erase the stars that gave birth to them, but they scatter the seeds of new stars and planets. They light up galaxies for a brief time, but their remnants persist for ages. Their shockwaves compress interstellar clouds, triggering the formation of new stellar nurseries. Without their violence, galaxies would stagnate, and life could never arise. In the deaths of massive stars, the universe renews itself. To us, collapse seems like an ending, but in the grand view of the cosmos, it is a transformation. The atoms in your body, the iron in your blood, the calcium in your bones, were once part of stars that ended in fire. Without their collapse, you would not exist to ponder their fate. Gravity wins the battle inside every star, but in its victory, it creates the possibility of everything else. Now we must follow the story deeper. We have seen the collapse itself, the fury of supernovae, and the scattering of matter across space. But what of the strange objects left behind? What of the neutron stars, where matter is crushed to densities beyond imagination, and the black holes, where even light cannot escape? The next chapter begins not with destruction, but with the birth of something new, the emergence of neutron stars, the lighthouses of the cosmos, born from collapse itself. When the fury of a massive star's collapse has passed, when its outer layers have been blasted into space in a supernova, what remains at the center can be something unlike any other object in the universe. The blast that lights up galaxies is only the outward sign of a deeper transformation. Inside the wreckage lies a core so compressed that the very nature of matter has changed. This remnant is a neutron star, one of the strangest creations gravity has ever wrought. To understand what a neutron star is, one must first imagine the collapse that forged it. In those final moments, the pressure was so extreme that electrons and protons were crushed together, merging into neutrons. What had once been atoms with familiar structures, nuclei surrounded by clouds of electrons, was stripped down into a uniform sea of neutrons. The star's matter was reduced to its most basic components, compacted until a single teaspoon would weigh billions of tons. Gravity, in its relentless triumph, had created something entirely new, a city-sized star corpse, packed tighter than anything in our everyday experience. A neutron star is small. Its diameter is roughly 20 kilometers, no larger than a city, yet it contains more mass than the Sunday. The density is beyond comprehension. If you could stand on its surface, which you could not, because the gravity would crush you instantly, you would find that even a pebble would hit the ground with the energy of a nuclear weapon. The surface gravity is hundreds of billions of times stronger than Earth's, a force that nothing can resist. And yet, paradoxically, this tiny object is stable, balanced between the crushing inward pull of gravity and the outward push of neutron degeneracy pressure, a quantum law that forbids neutrons from occupying the same state. These objects are not only dense but dynamic. Many neutron stars spin rapidly, completing a rotation in fractions of a second. This rotation, combined with their intense magnetic fields, creates beams of radiation that sweep across space, like the beams of a lighthouse. When one of these beams happens to point toward Earth, we see it as a regular pulse of radio waves or light. These pulsing neutron stars are called pulsars, and their clockwork flashes can be so precise that they rival the accuracy of atomic clocks. They are cosmic lighthouses, flashing signals across the galaxy, reminders of the collapse that gave them birth. The magnetic fields of neutron stars are among the strongest in nature. Some are so intense that they can strip atoms apart from vast distances. A special class known as magnetars harnesses this extreme magnetism, releasing bursts of energy that can outshine entire galaxies for moments at a time. These eruptions, though brief, are some of the most powerful explosions the universe can produce, outside of supernovae themselves. In these bursts, we see the hidden power still lurking in the corpses of stars, a power born from gravity's relentless crush. And yet, despite their violence and strangeness, neutron stars are also laboratories. They reveal the limits of matter under conditions we cannot reproduce on Earth. Physicists wonder whether their cores hide even more exotic states, where neutrons themselves dissolve into quarks, creating a sea of particles that has not existed since the earliest moments after the Big Bang. In this way, every neutron star is not just a relic of a dead star, but a window into the fundamental nature of the universe. What began as collapse and destruction has produced something enduring. A neutron star may remain for billions of years, slowly cooling, but never collapsing further unless it is pushed past its limits. It is a monument to gravity's triumph and to the strange resistance of quantum laws. When we look at pulsars flashing in the night sky, we are seeing the graves of stars, but also their afterlife, a steady reminder that even in death, stars continue to shape the cosmos. The story of neutron stars does not end here, for while they are stable under most conditions, they exist on a knife edge, add more mass, and even the degeneracy of neutrons cannot resist gravity. Push them too far, and they collapse again, this time into something darker, something from which there is no return. But before we cross that threshold, we must linger on the astonishing nature of neutron stars themselves, for in their silence and their pulses lies the evidence of the most extreme battle gravity has ever won. The moment of collapse that gives rise to a neutron star is as close as nature comes to absolute violence. Yet what emerges is an object of perfect stability, balanced on the edge of physical law. A star, once spanning millions of kilometers, shrinks into a sphere smaller than a city. But the transformation is not simply one of size, it is a transformation of essence. The familiar world of atoms, with electrons orbiting nuclei, vanishes. In its place is matter, compressed until atomic structure itself ceases to exist. What remains is a sea of neutrons locked so tightly that they can only resist further collapse through the strange dictates of quantum mechanics. To glimpse what this means, imagine a single spoonful of neutron star matter. On Earth, it would weigh billions of tons, more than a mountain compressed into your hand. The gravity of the star is so fierce that any mountain on its surface would collapse in an instant, crushed to perfect flatness. Even light struggles near its surface, bending under gravity's influence so strongly that an observer would see much of the star at once, its far side wrapped into view. Time itself slows in such an environment, a distortion predicted by Einstein's theory of relativity and confirmed by our observations. The behavior of neutron stars is no less astonishing than their structure. Many of them spin at extraordinary speeds, completing hundreds of rotations each second. Their rapid spin and immense magnetic fields create beams of radiation that sweep across space. If Earth lies in the path of one of these beams, astronomers detect a pulse of radio waves or light every time the beam swings past. These pulsars are among the most precise clocks in the universe. Their timing is so regular that scientists use them to test the very fabric of space-time, searching for ripples called gravitational waves. The magnetic fields of neutron stars can be trillions of times stronger than Earth's. In rare cases, these fields grow so intense that the star becomes a magnetar. Magnetars are unstable, prone to violent eruptions of energy that can release more power in a fraction of a second than the sun emits in 100,000 years. These eruptions can distort Earth's own magnetic field even from tens of thousands of light years away. In such displays, we see the lingering fury of the collapse, bottled within a star corpse, yet capable of shaking galaxies. Even in their quiet phases, neutron stars are mysterious. Their interiors are inaccessible, hidden by crushing pressure. Scientists debate what lies at their cores. Some suggest that the neutrons may dissolve into their constituent quarks, forming a state of matter that existed only in the first moments after the Big Bang. Others propose even stranger possibilities, like hyperons, or particles yet undiscovered. Each neutron star drifting through the galaxy is a natural experiment in physics, at extremes no laboratory can reach. To study them is to look back into the earliest conditions of the universe. From Earth, we have seen their signals in many forms. Radio telescopes capture the rhythmic pulses of pulsars. X-ray observatories detect their searing heat and violent outbursts. Occasionally, two neutron stars collide, merging into a single object and releasing gravitational waves that ripple through space-time itself. These collisions forge elements like gold and platinum in quantities unmatched by any other process. When we measure the composition of our world, we are measuring the gifts of such cosmic unions written into the crust of our planet and the rings on our fingers. Neutron stars embody the paradox of collapse. They are born from destruction, yet they endure as beacons and laboratories. They are corpses, yet they pulse with life like rhythms. Their density defies imagination, but their stability is absolute. They are constant reminders that gravity, in winning its struggle against fusion, can create as well as destroy. Each flash of a pulsar, each flare of a magnetar, is a message from the depths of physics, telling us that collapse is not an end, but a transformation. And still, neutron stars are not the ultimate limit. There exists a threshold, a boundary, where even neutrons cannot resist gravity's crush. Above a certain mass, perhaps about 2 to 3 times the mass of the Sun, no pressure can withstand the pull. The neutron star will collapse again, falling into an abyss from which not even light can escape. This is the next chapter in gravity's tale, but before we reach it, we must linger still on the astonishing legacy of neutron stars, for they reveal to us not only the outcome of collapse, but the hidden order of the universe itself. The legacy of a neutron star is not only in its existence, but in the signals it sends across the galaxy. When the collapse ends and the neutron star is born, it often spins at incredible speed. Conservation of angular momentum, the same principle that makes an ice skater spin faster when pulling in their arms, dictates that as the star shrinks, its rotation accelerates. What once was a gentle rotation of a massive star becomes the dizzying whirl of a compact corpse, spinning dozens or even hundreds of times each second. With each rotation, its powerful magnetic field channels radiation outward in narrow beams. To an observer on Earth, the beams appear as regular flashes of light or radio waves. Thus, the neutron star reveals itself as a pulsar, a lighthouse sweeping the cosmic seas. These pulses are so steady that they serve as cosmic clocks. Astronomers track them to detect the faint tug of orbiting planets or the subtle warping of space-time by unseen masses. Some pulsars are millisecond pulsars, spinning hundreds of times each second with near perfect regularity. Their precision rivals our most advanced atomic clocks, making them invaluable tools for exploring the universe. They are not just remnants of collapse, they are instruments, natural beacons, that illuminate the unseen forces of gravity itself. The drama grows when 2 neutron stars share an orbit. Locked in a gravitational dance, they circle each other for millions of years, gradually spiraling closer as they radiate energy in the form of gravitational waves. At last they collide, releasing bursts of energy that rival supernovae. In these collisions, space-time quakes, sending ripples across the cosmos that we can now detect with observatories on Earth. In 2017, astronomers observed such a merger for the first time, capturing not only gravitational waves, but also light across the spectrum. From that single event, we confirmed that neutron star collisions forge gold, platinum, and other heavy elements in vast quantities. It was a moment when theory met observation, and the universe revealed another secret of its alchemy. There is more to neutron stars than pulses and collisions. Some exist as magnetars, whose magnetic fields are so strong that they twist and crack their surfaces. When this happens, the release of energy is staggering. A single flare can momentarily outshine all the stars in its galaxy. These flares travel across space, bathing everything in their path with radiation. If a magnetar erupted close enough to Earth, it could strip our atmosphere in an instant. That no such event has yet occurred nearby is a fortune we seldom consider. In the behavior of magnetars, we see both the power of collapse and the fragility of life in the cosmos. Despite their power, neutron stars are fragile in one respect. They exist only within a narrow range of mass. If a neutron star gains too much additional matter, perhaps by pulling it from a companion star, the delicate balance that holds it stable is broken. Neutron degeneracy pressure can resist gravity only up to a certain point. Beyond this limit, the star must collapse again, and in this second collapse, there is no remnant that we can easily imagine. Gravity wins entirely, and a black hole is born. Thus, neutron stars represent both an ending and a threshold. They are the last line of defense against gravity's hunger, the final form matter can take before even quantum law is overwhelmed. They are the guardians of a boundary, standing on the edge of the abyss. To study them is to see how far matter can go before it disappears into something we cannot see at all. As we close the chapter on neutron stars, we stand at that threshold. We have seen how stars die quietly, how massive stars collapse in fury, and how neutron stars rise from the wreckage as dense, pulsing remnants. But there is one more fate, a darker and more final destiny for the most massive cause. In the next chapter, we will cross that line and follow gravity past its ultimate triumph into the domain of black holes, where the very fabric of space and time caves in and escape becomes impossible. Every star that collapses walks a narrow path, balanced between the laws of physics and the hunger of gravity. For smaller stars, the journey ends in quiet embers, white dwarfs glowing faintly as they cool. For massive stars, collapse squeezes matter into neutron stars, dense and defiant, holding gravity at bay with the strange resistance of quantum mechanics. But even this defiance has limits. There is a threshold, a boundary written into the very structure of matter. Cross that line, and no pressure in the universe can resist. Cross that line, and the result is a fall with no bottom, a descent into the most mysterious objects ever conceived, black holes. To understand this threshold, imagine a neutron star balanced against its own weight. Gravity presses inward with unimaginable force, while neutron degeneracy pressure, the quantum law that forbids identical particles from occupying the same state, pushes outward. As long as the neutron star remains below a certain mass, these two forces are in stalemate. But add more matter, perhaps by siphoning it from a companion star, or by colliding with another neutron star, and gravity grows stronger. At roughly 2 or 3 times the mass of the Sun, the pressure can no longer hold. Neutrons collapse, the star shrinks, and gravity claims absolute victory. The collapse beyond this threshold is unstoppable. Unlike the formation of a white dwarf or neutron star, there is no new kind of particle to resist gravity. Protons, neutrons, electrons, none can survive the crush. The matter falls inward, deeper and deeper, and there is no known force to halt it. The star vanishes, replaced by a region of space where the pull of gravity is so intense that nothing, not even light itself, can escape. This is the event horizon, the point of no return. Once past this invisible boundary, every path leads inward. From the outside, the birth of a black hole is marked by silence. There is no explosion, no flash of light announcing the final collapse. Instead, the star simply disappears, hidden behind the veil of its own horizon. To distant eyes, it seems as though the collapse slows, the star freezing on the edge of visibility, time itself stretched by the gravity well. But to the matter falling inward, the plunge is swift and final. The boundary is crossed, and the star is gone. The event horizon is not a surface in any physical sense. It is a boundary defined by geometry, the line where escape velocity exceeds the speed of light. Outside the horizon, light can still climb out, though bent and stretched by gravity. At the horizon, light is trapped, circling endlessly. Inside, space and time curve inward toward a singularity, a point where density becomes infinite and our physics falters. Whether such singularities truly exist, or whether new laws of nature intervene, remains one of the deepest mysteries of science. The threshold of no return is absolute. Nothing that crosses it can escape, not even signals or information. Yet, paradoxically, black holes are not entirely invisible. The matter falling toward them heats as it spirals inward, forming an accretion disk that blazes with energy. Jets of particles may erupt from the poles, shooting into space at near light speed. In these displays, we glimpse the hidden violence of the collapse, even though the heart of the black hole remains forever beyond sight. It is here, at the threshold of no return, that gravity reveals its ultimate power. For billions of years, fusion and degeneracy pressures can hold it off. But in the end, for the heaviest stars, gravity always wins. The neutron star collapses, the horizon forms, and the star is erased from the visible universe. What remains is not matter as we know it, but a region of space defined entirely by mass, spin, and charge. A black hole is not a thing in the ordinary sense. It is an absence, a shadow, the pure geometry of collapse. As we step across this threshold in thought, we enter a realm where the rules of nature blur. What happens inside a black hole? Is there truly a singularity, or is there a new kind of physics waiting to be discovered? These are questions we cannot yet answer. What we do know is that every black hole is the grave of a star that once burned with light. And yet, as with every chapter in the story of collapse, these graves are also beginnings. The moment a neutron star tips over the threshold is a moment of no return. Imagine the weight of an entire sun compressed into a sphere only 20 kilometers across. Now imagine adding more mass, pulling gas from a nearby companion star, or merging with another neutron star in a cataclysmic collision. At first, the neutron star resists. Its degeneracy pressure holds firm, neutrons locked by quantum law into states that cannot be further compressed. But with each new fragment of mass, gravity tightens its grip. Eventually the scale tips, the pressure falters, the star yields, Once the collapse begins, there is nothing to stop it. Unlike the step from white dwarf to neutron star, there is no next rung on the ladder of matter, no deeper form of pressure waiting to resist gravity. Neutrons themselves dissolve, and space folds inward. From the outside, the collapse seems to stretch, time dragging as light struggles against gravity's pull. An observer at a distance would see the dying star frozen at the brink, fading and reddening as its last light escapes, never quite crossing the boundary. But for the matter itself, the fall is swift and absolute. In less than an instant, it plunges through the event horizon, the invisible boundary where escape velocity exceeds the speed of light. This horizon is the defining feature of a black hole. It is not a physical surface, not a wall one could touch, but a point in space-time where direction itself changes. Outside the horizon, there is still a path outward, still a chance for light to flee. At the horizon, every path bends inward. Inside, all trajectories lead to the singularity, the point where the laws of physics, as we know them, break down. The event horizon is therefore a one-way boundary, a cosmic trapdoor that admits all but releases none. The geometry of this region is extraordinary. Time and space, trade roles. To an outside observer, time appears to stop for anything falling in, but for the matter itself, time flows normally, while space collapses. This inversion is not a trick of perspective, it is the true structure of space-time, as described by Einstein's general relativity. The mathematics tells us that once inside, the singularity lies in the future of every particle, as unavoidable as tomorrow's sunrise. But what that singularity is, no one truly knows. Some physicists argue that the singularity is a real point of infinite density, where matter and energy are crushed to zero volume. Others suggest that this infinity is a signal of our ignorance, that quantum gravity, an as yet undiscovered theory, will reveal a more complete picture. Perhaps matter transitions into a new state. Perhaps space-time itself becomes quantized, granular at the smallest scales. Whatever the truth, we cannot see it. The horizon hides all. The interior of a black hole is cut off from the rest of the universe, its secrets locked beyond reach. Yet paradoxically, black holes are not completely dark. Matter falling toward them does not vanish quietly. It spirals inward, heating to millions of degrees as it collides and compresses in the growing accretion disk. This disk blazes with radiation, pouring light into the universe just before the matter is swallowed. In some cases, magnetic fields channel energy into narrow jets that erupt from the poles, hurling matter into space at nearly the speed of light. These jets can extend for thousands of light years, visible across entire galaxies. In them, we see the violent edge of the event horizon, a storm at the border of oblivion. To study a black hole is to study gravity unchained. For decades, they existed only as mathematical solutions, strange predictions of Einstein's equations. Today, we have seen their shadows directly, captured in radio images that reveal dark circles surrounded by glowing rings of light. We have listened to their collisions in the form of gravitational waves, ripples in space-time that pass through Earth with barely a whisper, yet confirm the violent embrace of black holes spiraling together. What was once speculation is now observation, proof that the threshold of no return is real. The story of stars does not end in black holes alone, but it is here that collapse reaches its most extreme conclusion. Neutron stars resist, but only up to a point. Add enough mass, and resistance fails. The horizon forms, the star disappears, and what remains is a region defined not by matter, but by the geometry of space-time itself. The universe writes its most mysterious chapter at this boundary, a chapter still unfolding, as we try to decipher what lies beyond. The threshold of no return is more than a physical boundary. It is a philosophical frontier, a place where our knowledge falters and imagination strains. For every other kind of stellar remnant white dwarfs, neutron stars, we can point to matter, to particles resisting gravity with pressure or with quantum law. But when a black hole is born, all such explanations vanish. The horizon hides everything. Beyond it, matter is no longer matter in any form we can describe. What remains is only mass, charge, and spin, the three simple numbers that define a black hole from the outside. The complexity of a star, its layers and elements, its turbulence and fire, all reduced to these few descriptors. A star that once blazed for millions of years becomes an object defined by silence. Yet silence does not mean insignificance. Black holes bend space and time around them in ways that ripple far beyond their horizons. Light bends, paths of stars curve, and even time itself slows in their presence. To circle a black hole is to orbit not merely an object, but a region of warped geometry. For those who fall inward, the passage of time differs from the universe outside. What seems a moment near the horizon can be an eternity for distant observers. In this distortion, we glimpse the strange elasticity of time itself, stretched and twisted by gravity's victory. The creation of a black hole is also the erasure of a star from the visible universe. When collapse crosses the threshold, there is no remnant to observe, no ember glowing in the dark, no shell of gas drifting outward as a nebula. The star is gone, replaced by a shadow. The accretion disk and jets may blaze, but the object itself hides absolutely, cloaked behind the horizon. To astronomers, the black hole reveals itself only by what it does to the world around it. The way stars orbit invisibly, the way light bends, the way matter disappears in sudden flares. The presence of absence becomes proof. What happens to information about the star that formed the black hole is one of the greatest puzzles in physics. Does the history of that star vanish forever, erased from the fabric of reality? Or is it somehow encoded in the horizon, preserved in ways we do not yet understand? This is the information paradox, a riddle that has challenged physicists for decades. Some argue that quantum theory demands that no information is lost, while general relativity insists that the horizon permits no return. At this boundary, two great pillars of modern physics collide, reminding us that our knowledge is not complete. For the stars that reach this end, the outcome is absolute. There is no turning back, no second chance. Once the horizon forms, the collapse is finished, the story of that star concluded. But in another sense, a new story begins. Black holes are not dead ends of the universe. They are engines of cosmic transformation. They can power quasars, those dazzling beacons at the hearts of galaxies that shine brighter than all their stars combined. They can merge with one another, shaking the fabric of space-time itself. In their silence, they exert influence on scales larger than the stars that birthed them ever could. The threshold of no return is therefore not an ending, but a doorway. It is the passage from the familiar to the unknown, from matter we can touch to geometry we can only imagine. To stand at the edge of a black hole, if such a thing were possible, would be to look into the future of physics itself, into a domain where our laws are incomplete. The collapse of stars shows us that the universe does not stop where our understanding stops. Instead, it invites us forward, into mystery. And so we leave the neutron stars behind. We have followed their birth, their pulses, their strength, and their fragility. We have watched them reach their limit and yield to gravity's final demand. Now, as we cross the threshold, we must descend into the realm where gravity is unchained, where horizons conceal singularities, and where collapse becomes not just the end of a star, but the foundation of cosmic power. The next chapter belongs to black holes. A black hole is unlike any other object in the cosmos. It is not a star, not a planet, not even a remnant in the traditional sense. It is an absence, a region of space where gravity has triumphed so completely that even light cannot escape. To speak of a black hole is to speak of boundaries, for what we observe is not the interior but the horizon, the invisible veil, beyond which nothing can return. Yet though hidden, black holes announce themselves with power. They shape the motions of stars, blaze with accretion disks, and hurl jets across interstellar space. They are gravity unchained, and they are among the most extraordinary legacies of stellar collapse. From the outside, a black hole is deceptively simple. It is defined by only three numbers: its mass, its spin, and its electric charge. Everything else about the star that collapsed, its size, its layers, its chemistry, is erased, hidden behind the horizon. What remains is pure geometry. The horizon itself is a sphere, the boundary where escape velocity equals the speed of light. Cross that line, and the path outward no longer exists. To distant eyes, anything approaching the horizon slows and fades, never quite vanishing, stretched into eternity by the warping of time. But to the object itself, the fall is swift, inevitable, and final. Inside the horizon, space-time curves toward the singularity. According to general relativity, this singularity is a point of infinite density, where matter is crushed into zero volume. Such infinities are unsettling, for they suggest the failure of our physics. Perhaps the singularity is real, a place where our concepts of space and time dissolve. Or perhaps it is a sign that new laws await, a deeper theory that unites gravity with quantum mechanics. For now, we cannot know. The horizon conceals all. Yet even if the interior remains hidden, the edges of black holes are anything but quiet. Matter that falls toward them rarely plunges directly inward. Instead, it spirals, forming an accretion disk that glows with unimaginable heat. Friction and compression within the disk accelerate particles to extreme velocities, releasing torrents of radiation. To telescopes, these disks appear as blazing beacons, brighter than entire galaxies. In some systems, magnetic fields twist the inflowing matter into jets that erupt from the poles, shooting particles outward at nearly the speed of light. These jets stretch for thousands of light years, visible across cosmic distances. It is in these displays that black holes reveal their paradoxical nature. Though nothing escapes from within the horizon, the approach to that horizon can be spectacularly luminous. A star wandering too close may be shredded by tidal forces, its matter stretched into streams that spiral into the disk. For a time, the black hole feasts, and the light of its banquet reaches across the universe. Such events remind us that even the darkest objects in nature can become sources of brilliance, their presence marked by the destruction they cause. The confirmation of black holes as real, not merely theoretical, is one of the triumphs of modern astronomy. For decades, they lived in equations, solutions to Einstein's theory of relativity that seemed too strange to exist. Then came the evidence. Stars at the centers of galaxies, orbiting invisible masses, millions of times heavier than the Sunday X-ray emissions from binary systems where one star is torn apart by a hidden companion. And most recently, images of their shadows, captured by networks of telescopes, spread across Earth, revealing dark circles rimmed with glowing light. Black holes have stepped from theory into reality, and with them, the boundaries of our understanding have expanded. In their silence, black holes dominate. They anchor galaxies, dictate the motions of stars, and carve the evolution of cosmic structures. They are the final expression of gravity's power, where collapse does not halt, where matter and light alike are trapped. To study them is to confront the limits of physics, the edge where questions outnumber answers. And yet, they are also central to the story of creation. Without black holes, galaxies would not form as they do, and the universe would be a different place. What began as the collapse of a single star becomes something far greater. Black holes outlast their progenitors, growing as they consume matter, merging with others, shaping the cosmos on grand scales. In them, we see not only the victory of gravity, but its capacity to sculpt the very architecture of the universe. The threshold of no return was the crossing point. Now we have stepped into the realm where gravity reigns without opposition, and the story only deepens. The mystery of black holes deepens the closer we look. Around their horizons, physics bends into paradox. Imagine drifting near one, watching the universe distort before your eyes. Light from distant stars would bend and twist, forming strange halos. Time would slow, your heartbeat stretching into eternity as you approached the horizon. To those far away, you would seem to freeze, your last signals fading into red twilight. Yet for you, the plunge would be sudden, the crossing of the horizon unnoticed, a step taken without drama until it was too late. In this duality, we see the strangeness of space-time laid bare. The singularity at the core of a black hole is perhaps the most haunting feature of all. According to Einstein's equations, all the matter of the collapsed star falls into a single point of infinite density. But infinities in physics are warnings, signals that our theories are incomplete. Perhaps the singularity is a real object, a point where space and time end. Or perhaps quantum mechanics intervenes, weaving a new fabric of reality beyond our grasp. Some physicists imagine that matter may transform into exotic states, a fluid of quarks, or even stranger particles, hidden forever inside the horizon. Others wonder if the singularity could connect to other regions of space-time, doorways to universes beyond our own. These ideas remain speculation, for no signal can escape to confirm them. The black hole guards its secrets absolutely. Even without peering inside, black holes shape the cosmos with their power. The accretion disks around them blaze with ferocity, some radiating more energy than 1 trillion suns. Matter spirals inward, colliding, compressing, heating to millions of degrees. Magnetic fields twist and knot, funneling particles into jets that pierce galaxies. These jets can stretch for thousands of light years, visible across intergalactic distances as threads of light against the dark. They sculpt their surroundings, stirring gas, triggering or suppressing the birth of stars. In these ways, black holes are not just graveyards, but architects, shaping the evolution of galaxies on grand scales. Nowhere is this influence clearer than in the hearts of galaxies, where supermassive black holes reside. These giants, millions or billions of times heavier than the Sun, anchor their host galaxies. Around them, stars orbit in dizzying swarms, bound by gravity's invisible chain. When fed with infalling matter, they ignite as quasars, some of the brightest objects in the universe. Quasars can outshine all the stars of their galaxies combined, their light traveling across billions of years to reach us. To gaze at one is to look back into the earliest epochs of the cosmos, when black holes first carved their influence into the young universe. Despite their apparent simplicity, black holes challenge the foundations of science. General relativity describes their geometry with elegance, but quantum theory whispers contradictions. At the horizon, questions of information and entropy arise. Can the details of what falls into a black hole ever be truly lost? Or is it preserved somehow, encoded in subtle patterns at the edge? This information paradox has driven decades of debate, pitting two great theories against each other. The resolution may lead us to a new understanding of reality, one that unites the laws of the very large with those of the very small. Our knowledge of black holes is no longer abstract. In recent years, we have captured their images directly, mapping the shadow of the horizon in glowing rings of light. We have heard their collisions through gravitational waves, ripples in space-time that vibrated through Earth itself. Each discovery brings black holes from theory into experience, confirming their presence as actors on the cosmic stage. And yet, with every answer, deeper mysteries emerge. What lies at the singularity? How do horizons store information? Is the black hole truly the end, or a bridge to something beyond? Black holes are the ultimate expression of collapse, the places where gravity is set free from all resistance. They are terrifying in their finality, yet they are also luminous in their influence, shaping galaxies and seeding the cosmos with energy. In their silence lies power, in their darkness lies creation. They are the culmination of the struggle that begins in every star, the final act of gravity's relentless play. And as we study them, we stand on the edge of understanding, our minds pressed against the horizon, wondering what lies within. To speak of black holes is to speak of paradox. They are regions where nothing escapes, yet they can power the brightest beacons in the universe. They are formed from collapse and erasure, yet they shape the growth of galaxies on scales that span billions of years. They are defined by simplicity, just mass, spin, and charge, yet they conceal mysteries that cut to the very heart of physics. Every black hole is both an end and a beginning, a silence and a roar. The role of black holes in galactic life cannot be overstated. At the centers of most galaxies, including our own Milky Way, lurks a supermassive black hole. Stars whirl around it in tight orbits, moving so fast that only an invisible mass, millions of times greater than the Sun, can account for their paths. For the most part, this central monster slumbers, quiet and unseen. But when streams of gas spiral inward, it awakens. The accretion disk forms, jets erupt, and the galaxy itself feels the consequences. Quasars, blazing from the hearts of young galaxies, are powered by such awakenings. They shine across cosmic distances, their light arriving on Earth after journeys of billions of years. In them, we glimpse the role of black holes as engines of cosmic evolution. These engines are not only destructive but also creative. The energy they release can trigger the formation of new stars by compressing nearby gas clouds, or suppress it by blasting gas away and halting star birth. In this way, black holes regulate the growth of galaxies, acting as both predators and gardeners. Their influence stretches far beyond their horizons, far beyond even their host galaxies, shaping the cosmic web itself. They are sculptors working in silence, carving the grand patterns of the universe. And yet, despite their dominance, black holes remain incomplete in our understanding. The singularity mocks us with its infinity, demanding a deeper theory. The horizon teases us with questions of information and entropy. Even Hawking radiation, the faint whisper predicted to leak from black holes through quantum processes, remains undetected, waiting for proof. Each mystery reminds us that collapse has carried us to the frontier of knowledge, to the place where current physics yields and new physics must emerge. Still, what we do know is enough to inspire awe. Black holes are not merely exotic footnotes in the story of stars. They are central characters in the drama of creation. They are born from collapse, but they endure as anchors of structure. Without them, galaxies would not form as they do. Without them, the history of the cosmos would unfold along a different path. They are both the consequence of stellar death and the architects of cosmic life. In their gravity, we see nature unrestrained. In their silence, we see the promise of discovery. In their shadows, we see reflections of our ignorance, and in their influence, we see the scale of the universe itself. Black holes are the culmination of the story that began with the struggle of gravity and fusion in the heart of stars. When fusion fails, when even neutrons cannot resist, gravity takes everything, bends space-time into wells without bottom, and writes its legacy into the shape of galaxies. The journey of collapse does not end here. Black holes may be the most extreme outcome, but they are not the only legacy of stellar death. Every supernova, every neutron star, every black hole contributes to the cycle of matter and energy that drives the universe forward. In the next chapter, we will step back from individual deaths and examine the grand design. We will see how collapse seeds the cosmos with heavy elements, how explosions trigger new stars, how remnants shape galaxies, and how life itself is possible only because stars die. Collapse is destruction, but it is also creation, and its role in the universe is far greater than any single star. Every death in the cosmos leaves a legacy: a white dwarf cooling in silence, a neutron star pulsing like a beacon, a black hole bending space-time with invisible gravity. Each is more than an end. The collapse of stars is not simply destruction, it is the mechanism by which the universe renews itself. Without death, there would be no rebirth. Without collapse, there would be no planets, no oceans, no life. It is in the violence of endings that the seeds of beginnings are scattered. Consider the elements in your body: the calcium in your bones, the iron in your blood, the oxygen in your lungs. All were forged in stars. Hydrogen and helium came from the birth of the universe itself, but everything beyond was created in furnaces of nuclear fire. Ordinary stars like the sun built carbon and nitrogen in their cores and shared them through gentle winds and planetary nebulae. More massive stars created oxygen, silicon, and sulfur in their final burning stages. But the heaviest elements, gold, platinum, uranium, were born in the most violent events of all: supernovae and neutron star collisions. Without these deaths, the universe would be a barren expanse of hydrogen and helium, a canvas without colors. Supernovae play the starring role in this cosmic alchemy. When a massive star explodes, its shockwave smashes atoms together in a frenzy, forging elements far heavier than iron. In mere seconds, the star manufactures a library of new atoms, scattering them outward at thousands of kilometers per second. These elements spread into the interstellar medium, mixing with clouds of gas and dust. Over time, those enriched clouds collapse into new stars and planets. The iron in a sword, the silicon in a computer chip, the gold in a ring, all of it was born in the collapse of stars. Each explosion is a gift, a distribution of raw material for the future. This process transforms not only chemistry but structure. The shockwaves of supernovae ripple outward for hundreds of light years, stirring the interstellar medium like a stone cast into a pond. These ripples compress clouds of gas, triggering new bursts of star formation. In this way, death begets life on a galactic scale. One generation of stars dies, and from their ashes, a new generation is born, enriched with the elements of complexity. This cycle has repeated for billions of years, weaving the fabric of galaxies into living ecosystems. The Milky Way itself is a tapestry of such cycles. Within its spiral arms lie clouds enriched by countless supernovae, glowing nurseries where new stars ignite. Each bright cluster is a testament to ancient deaths. Without those deaths, there would be no Earth, no oceans, no forests, no humans gazing upward. Life is not an accident, apart from collapse. It is collapse made manifest. The destruction of stars carved the conditions for our existence. Seen in this light, stellar death is not merely the end of an individual story, but the continuation of a cosmic narrative. Every atom forged in a star carries that story forward. When we breathe, when we speak, when we look at the night sky, we are participating in it. We are the aftermath of collapse, the descendants of explosions, the quiet echoes of ancient stars. And yet, the role of stellar death is even larger than chemistry and biology. It extends to the very architecture of the universe. Supernovae sculpt galaxies, regulate star formation, and distribute matter across vast distances. Neutron stars and black holes, born from collapse, add their influence, bending space-time and shaping cosmic flows. In their combined actions, we see that death is not a side effect, but the engine of cosmic evolution. This is the paradox at the heart of collapse. The universe depends on destruction. Without the deaths of stars, there would be no diversity of elements, no renewal of star formation, no galaxies shaped by feedback, no worlds rich with possibility. To grasp this truth is to see that every ending is also a beginning, written in the language of gravity and fusion. The legacy of stellar death reaches far beyond the scattering of elements. When stars collapse, they leave behind remnants that continue to shape the cosmos long after the explosions fade. Neutron stars, black holes, and even white dwarfs exert influence that ripples across space and time. Their presence governs the birth of new stars, the motion of galaxies, and the very balance of the universe itself. To understand the cosmos is to recognize that death is not a final act, but a force of transformation. Neutron stars are one such legacy. Born in the crucible of collapse, they flash across the galaxy as pulsars, their beams sweeping space like cosmic clocks. These pulses are more than curiosities, they are tools. Astronomers use their precise timing to probe the fabric of space-time itself, to detect gravitational waves rippling from distant cataclysms, to measure the warping of gravity with unmatched precision. Neutron stars, though small and faint, are instruments in the hands of the universe, revealing truths that no living star could show. Their collisions, rare but titanic, forge gold and platinum, seeding the cosmos with treasures that endure in the crust of planets and the rings of human hands. Black holes, the darker heirs of collapse, extend this influence on grander scales. They anchor galaxies, their gravity binding billions of stars into spirals and ellipses. At the centers of galaxies, supermassive black holes regulate star formation, their outbursts shaping the rhythm of growth and silence. When they awaken, they ignite as quasars, blazing so brightly that they can be seen from across the observable universe. In their jets and outflows, they drive matter outward, stirring intergalactic gas and regulating the birth of new stars. Without them, galaxies might collapse inward unchecked or spread chaotically without order. Black holes, born of collapse, become the architects of cosmic design. Even the gentler remnants, white dwarfs, play their part. When paired with companion stars, they can siphon matter until they reignite in thermonuclear explosions, known as Type I supernovae. These explosions, though less violent than core collapse supernovae, shine with predictable brightness. Astronomers use them as standard candles to measure distances across the universe, charting the expansion of space-time itself. It was by observing these deaths that scientists discovered the accelerating expansion of the cosmos, a revelation that led to the concept of dark energy. In this way, even the quiet corpses of stars can reveal the grandest truths. Stellar death also governs the recycling of matter in galaxies. Without explosions and outflows, gas clouds would collapse only once, forming a generation of stars that would quickly exhaust their fuel. Instead, supernovae enrich the medium, returning heavy elements and stirring clouds into new structures. The cycle of death and rebirth ensures that galaxies remain active, forming stars across billions of years. Our own Milky Way carries this history in its spiral arms, each wave of stars born from the ashes of the last. Collapse is not an interruption, but the mechanism by which time itself unfolds in galaxies. Life itself is one of the quietest but most profound consequences of stellar death. Without carbon from red giants, oxygen from massive stars, and iron from supernovae, the chemistry of biology could not exist. Planets like Earth would never form, oceans would never flow, cells would never arise. To breathe is to inhale the memory of stars. To live is to carry collapse within. Our blood carries the iron forged in supernovae, our bones the calcium born in stellar cores, our thoughts the energy of atoms assembled in long-dead stars. The death of stars is written into us at every level. And yet, stellar death is not uniform. Each outcome, white dwarf, neutron star, black hole, adds a unique note to the cosmic symphony. Each pathway enriches the universe differently, providing light, matter, energy, or gravitational influence. Together, they weave the fabric of existence, turning collapse into a driving force of creation. The universe is not a static expanse, but a living cycle, and that cycle depends on death as much as on birth. In this, we find the profound truth: destruction is not the enemy of creation, but its partner. The end of one star sets the stage for countless beginnings. The collapse of matter becomes the foundation of structure. The silence of remnants becomes the pulse of galaxies. Death, far from being a void, is the hidden engine that propels the cosmos forward. The cycle of stellar death is the cycle of the universe itself. Every cloud of gas that collapses into stars carries within it the ashes of ancient suns. Every planet that forms from dust is enriched by elements forged in explosions long past. Every living creature is a mosaic of atoms with cosmic ancestry. When we trace this lineage backward, we arrive not at silence, but at collapse, at the deaths of stars that gave their substance to the future. The universe is not built upon permanence, but upon transformation, and transformation is written in the language of endings. Galaxies too owe their beauty to this cycle. Without stellar deaths, the interstellar medium would stagnate, its hydrogen and helium locked forever in stars, with no chance of renewal. But explosions return matter to the galactic sea, stirring it, mixing it, seeding it with heavy elements. Spiral arms gleam with new stars, only because older generations have burned, collapsed, and passed on their legacy. Even the great dark clouds, pregnant with starbirth, are colored by the light of past deaths. Galaxies are ecosystems, and death is their essential nutrient. The paradox of collapse is that it feels like loss, but acts as creation. To the star itself, collapse is annihilation, a defeat where gravity wins and the furnace of fusion is extinguished. But to the universe, collapse is generosity. It provides the building blocks for planets, the triggers for new stars, the engines for galactic architecture. Even black holes, those silent tyrants of gravity, are essential. They sculpt galaxies, regulate growth, and serve as cosmic anchors. Death is not incidental, it is the scaffolding of existence. On Earth, we feel this paradox, without always recognizing it. The gold we prize, as rare treasure, was forged in a neutron star collision billions of years ago. The oxygen we breathe was created in the dying throes of massive stars. The silicon in our computers, the calcium in our bones, the iron that carries life through our blood, all of it comes from stellar death. The cosmos has written its history into our very being. We are the children of collapse, and our lives are the continuation of a story that began in the hearts of stars. It is easy to imagine that collapse is an end, a silence where once there was light. But the deeper truth is that collapse is the renewal of the cosmos. Each white dwarf, each neutron star, each black hole carries forward the memory of a star that lived and died. Each supernova is both an obituary and a birth announcement, scattering the ingredients for new worlds while erasing the old. The universe endures, not in spite of stellar death, but because of it. And so the story continues. We have followed collapse, from the quiet fading of ordinary stars to the violent explosions of massive ones, from the birth of neutron stars to the creation of black holes. We have seen how these remnants shape galaxies, seed elements, and make life itself possible. But collapse has even more dramatic forms, reserved for the most massive stars of all. There are deaths so violent that nothing remains, stars so large that even black holes are not left behind. These are the extreme cases, the rare and catastrophic ends that reveal collapse in its most unrestrained form. In the next chapter, we will walk into that realm of extremes. We will witness stars that obliterate themselves entirely in pair instability supernovae, leaving no remnant, no core, only energy and ashes. We will see hypernovas, explosions more powerful than supernovae, capable of producing gamma-ray bursts, beams of energy that could sterilize entire worlds. In these rare fates, gravity and physics collide in spectacles so intense that they challenge our very understanding of collapse. The story grows darker, stranger, and more violent, but it remains the same story, gravity claiming victory, and the universe remaking itself in the fire of endings. Most stars follow familiar paths to their ends. Small ones fade quietly into white dwarfs, middleweights swell into red giants before settling into embers, and massive ones collapse into neutron stars or black holes. Yet nature is not bound to the ordinary. There are stars so enormous, so heavy, that their deaths are unlike anything else in the universe. These are the titans of stellar evolution, with masses well above 100 times that of the Sunday. Their lives are short, only a few million years at most, but their deaths are among the most spectacular events ever conceived. In them, collapse does not merely create remnants. In them, collapse can mean annihilation. One such fate is the pair instability supernova. To understand it, imagine a star of staggering mass, burning at temperatures so high that the very photons inside carry enough energy to create particles. When a gamma ray in the star's core collides with matter, it can transform into an electron and its antimatter twin, a positron. This process robs the star of the radiation pressure that once held gravity at bay. Instead of supporting the core, the photons vanish into pairs and the balance tips. Gravity seizes the star and collapse begins. But the collapse does not proceed as in ordinary massive stars. Instead, the sudden compression triggers runaway fusion. Oxygen and silicon ignite violently, producing more energy than the star can contain. In an instant, the entire star detonates. The explosion is not a supernova in the traditional sense, where only the outer layers are expelled. It is total destruction. No neutron star, no black hole, no remnant of any kind remains. The star is obliterated, its matter hurled outward into the cosmos, its energy flooding space in a blinding burst. The violence of a pair instability supernova is almost beyond comprehension. The energy released can exceed that of a normal supernova by factors of 10 or more. The explosion can be visible across billions of light years, outshining entire galaxies for weeks at a time. Unlike ordinary supernovae, which leave behind compact corpses, these events erase the star completely, scattering every atom into space. They are rare, requiring initial masses far larger than most stars ever achieve, but they remind us that collapse can be final in the most literal sense. For the cosmos, such an event is both tragedy and gift. The obliteration means no neutron star, no black hole, no remnant to continue the story. But the scattering of elements is immense, enriching the interstellar medium with heavy atoms on scales unmatched by other deaths. A single pair instability supernova can seed its surroundings with enough material to spark new generations of stars and planets rich in metals. Entire clusters may owe their chemistry to the sacrifice of a single star that burned too brightly, too briefly, and ended in complete destruction. Yet pair instability is only one extreme. There are also hypernovas, explosions of massive stars that do collapse, but with far more violence than ordinary supernovae. Hypernovas often occur when a massive, rapidly rotating star collapses into a black hole. The collapse channels enormous energy into narrow beams, producing gamma-ray bursts, jets of radiation so intense that they can sterilize entire regions of galaxies. These bursts, though lasting only seconds, are the brightest explosions we know, visible across the observable universe. In them, collapse becomes a weapon of light, cutting across cosmic distances with destructive brilliance. These extremes remind us that not all collapse follows the same script. In most cases, the battle between gravity and pressure ends with balance, with remnants left behind to whisper the story of their parent stars. But in these rare fates, gravity drives the drama to its ultimate conclusion. Either the star obliterates itself entirely, leaving no trace, or it collapses with such violence that it reshapes space and floods the cosmos with radiation. In both, we see the unrestrained power of collapse, a reminder that the universe still holds secrets capable of humbling imagination. The stars that face these ends are rare, but their role in the universe is profound. Their explosions are beacons, their ashes the seeds of future worlds. Their deaths remind us that collapse is not a single path but a spectrum, ranging from quiet fades to annihilations that echo across the universe. They are the universe at its most extravagant, where destruction reaches its most creative extremes. The hypernova is collapse, magnified to its most violent form. Where a supernova already rivals the brightness of an entire galaxy, a hypernova exceeds even this, releasing 10 times as much energy in a single event. It is the death of a massive, rapidly rotating star, a giant whose mass is dozens of times greater than the Sunday. When fusion can no longer resist gravity, the collapse is not only inward, but also channeled by rotation and magnetic fields. Instead of dispersing evenly in every direction, the energy finds narrow escape routes along the star's poles. The result is a pair of jets, tightly focused, bursting outward at nearly the speed of light. In these jets lies one of the universe's most spectacular phenomena, the gamma-ray burst. For a few seconds, these beams shine brighter than the combined light of all the stars in billions of galaxies. To an observer unlucky enough to be in their path, the burst would outshine the entire night sky, flooding space with radiation that could strip atmospheres and sterilize planets. Fortunately, gamma-ray bursts are rare, and their beams are narrowly focused, but they remind us that the death of a star can unleash power on scales that defy human imagination. The mechanics of a hypernova are still studied with awe and uncertainty. As the core collapses, a black hole forms at the center, surrounded by an accretion disk of infalling material. The rotation of the collapsing star winds magnetic fields into immense structures, accelerating particles to near light speed. The jets bore through the outer layers of the star, erupting into space with titanic force. Once free, they shine as gamma rays, their brilliance reaching across the universe. Even when the light has faded, the afterglow continues for days or weeks, painting the sky with the fingerprints of the elements forged in the blast. These events are more than displays of violence. They are acts of creation. In the inferno of a hypernova, new heavy elements are born. The shockwaves enrich the galaxy, seeding star, forming clouds with the ingredients of planets and life. Just as ordinary supernovae scatter iron and oxygen, hypernovae scatter gold and uranium, extending the cosmic library of elements. Collapse, even in its most ferocious forms, continues to play its role as the architect of existence. The reach of a gamma-ray burst is staggering. Some scientists speculate that such an event, occurring within a few thousand light-years of Earth, could have influenced the history of life on our planet. A burst directed at Earth would have bathed the atmosphere in radiation, breaking apart molecules, destroying the protective ozone layer, and exposing the surface to deadly ultraviolet light. From the sunday, life might struggle, species might vanish, and evolution might be redirected. While no evidence ties a known extinction directly to a gamma-ray burst, the possibility underscores how closely our fate is bound to the violent deaths of stars. To observe a hypernova is to look back into the early universe. Most of the bursts we see come from galaxies billions of light-years away, their light traveling since the cosmos was young. They tell us that massive stars lived and died even when galaxies were just beginning to form. Their brilliance reaches us as messages from the past, reminders that collapse has shaped the universe from its earliest days. In their afterglows, we read the chemical evolution of galaxies and the birth of complexity long before Earth existed. Hypernovae and gamma-ray bursts are rare, but their impact is immense. They show us that collapse can be directional, focused into beams that pierce the cosmos. They reveal that destruction can echo across billions of years, carrying the story of a star's death to distant observers. They remind us that collapse is not uniform, that its extremes can defy expectations and stretch our understanding. In these events, the universe reveals its most extravagant expressions, moments when gravity's triumph becomes spectacle on a cosmic stage. Yet even in these extremes, the theme is familiar. Gravity pulls inward, fusion falters, collapse begins. The outcome may be total annihilation, as in pair instability supernovae, or ferocious jets, as in hypernovae. But the principle is the same. When fusion fails, gravity wins. The result may light up the universe or scatter its ashes, but always the process is creation through destruction. The universe does not favor extremes, but it allows them. Most stars will never know the fates of pair instability or hypernova collapse. Yet those that do leave imprints far larger than their numbers. A single pair instability supernova can outshine an entire galaxy, erasing its parent star completely and scattering heavy elements in abundance. A single hypernova can send gamma-ray beams across billions of light-years, visible long after the star itself has vanished. In both, we see collapse pushed to its ultimate limits, showing us what happens when mass and gravity cross thresholds few stars ever reach. These rare deaths are reminders that the cosmos thrives on variety. Not every star follows the quiet pathways of white dwarfs, nor even the familiar routes of neutron stars and black holes. Some burn too brightly, live too fast, and end in ways that redefine destruction. Pair instability leaves nothing behind, no remnant to carry on the legacy, only light and expanding shells of matter. Hypernovae collapse into black holes, but not before unleashing energies that dwarf even the mightiest supernovae. In both cases, the ordinary rules bend, and collapse becomes not a whisper or a roar, but a scream across the fabric of space-time. The consequences ripple outward. Entire star-forming regions can be transformed by such explosions, enriched with new elements, or blasted into turbulence that sparks waves of birth. Gamma-ray bursts, if aimed at a nearby planet, could change the trajectory of life itself. Perhaps somewhere in the galaxy, civilizations never had the chance to rise because a beam from a dying giant erased the possibility. The universe is not only generous with creation, but ruthless with destruction, and the balance between the two defines the history of galaxies. And yet, even these extremes follow the same truth. Collapse is never meaningless. The obliteration of a star is also the enrichment of the cosmos. The fury of a gamma-ray burst is also the scattering of ingredients that will one day form new worlds. The absence left by a pair instability death is also the presence of matter woven into nebulae. The violence is creative, the destruction constructive. In the harshest fates, the cosmos finds its most extravagant ways to recycle itself. For us, these extremes are distant spectacles. They are rare enough that our galaxy has not seen one in recorded history, though evidence suggests they happened often in the early universe. But their rarity does not diminish their importance. They show us the boundaries of what stars can become, the outer edges of the possible. They teach us that the laws of physics, though universal, can manifest in wildly different ways, depending on scale and mass. They remind us that collapse is not one story but many, each with its own ending, each with its own contribution to the grand narrative of the cosmos. As we close the chapter on extremes, we are left with a sense of awe and humility. The universe contains not only the ordinary and the expected, but the rare and the astonishing. Some stars die quietly, some in violent bursts, and a few in ways that erase them completely or unleash beams that span the universe. Collapse is diverse, collapse is creative, collapse is unrelenting. But the story of gravity crushing stars does not end with stars alone. Collapse is a process written into the very fabric of matter, a question of how pressure resists gravity and where the limits lie. Beyond white dwarfs, beyond neutron stars, beyond black holes, there are speculations of stranger objects still. Could collapse give rise to quark stars, where neutrons themselves dissolve? Could space-time harbor gravastars, or other exotic remnants that defy our current understanding? The path of collapse leads us to ask what lies beyond the known, to wonder whether even more bizarre states of matter await in the hidden corners of the cosmos. The next chapter carries us past stars into the realm of speculation. We will ask, what happens when collapse goes further, when physics is pushed beyond familiar limits? We will explore the frontier of astrophysics, where theory reaches into the unknown, and where the story of gravity's triumph may hold still more surprises. The collapse of stars has already taken us from the gentle fading of white dwarfs to the crushing densities of neutron stars, and finally, to the abyss of black holes. Each step marks gravity claiming a greater victory, each remnant a deeper concession by matter. But even here, at the limits we know, the story may not be finished. Physics itself suggests that collapse might yield stranger outcomes still, objects not yet confirmed by observation, but whispered by theory. The universe has always proven more inventive than our imagination, and where matter is forced to its limits, new possibilities emerge. Consider the neutron star, a sphere of unimaginable density, where neutrons themselves shoulder the weight of gravity. But neutrons are not fundamental. They are made of quarks, bound together by the strong nuclear force. If gravity presses harder still, perhaps the neutrons will dissolve, their quarks set free to form a new state of matter, quark matter. In such a star, called a quark star, matter would be stripped to its most elementary components, a sea of up and down quarks, perhaps even strange quarks, packed into a density beyond anything in a neutron star. The physics of such objects is uncertain, but their existence is not impossible. They would be smaller than neutron stars, denser, darker, their surfaces less like matter as we know it, and more like alien terrain where the rules of chemistry no longer apply. If quark stars exist, they would be rare, transitional, formed in the narrow window between neutron stars resisting collapse and black holes conquering all. Their signals might mimic neutron stars, but with subtle differences in their radiation or rotation. Some observations hint at candidates, stars too compact to be explained easily by neutron matter alone, yet proof remains elusive. For now, quark stars live in the realm of theory, shadows of possibility, at the edge of collapse. Beyond quark stars lies speculation even more radical. Some physicists have proposed gravastars, gravitational vacuum stars, objects where collapse halts just before forming a black hole. In these ideas, the core is not singularity, but exotic energy, balanced by a thin shell of matter at the edge. Such objects would mimic black holes from afar, their horizons indistinguishable, but their interiors would differ profoundly. If gravastars exist, they could resolve puzzles like the black hole information paradox, offering an escape from the infinities that haunt relativity. But like quark stars, gravastars remain hypothetical, glimpses of what might be possible when gravity and quantum physics meet. The very act of collapse forces us to confront the unknown. General relativity, magnificent in its description of black holes, cannot alone describe the behavior of matter at densities beyond neutron stars. Quantum mechanics, triumphant in the microscopic realm, cannot easily stretch to the cosmic scale of collapsed stars. Where the two meet, at the boundary of collapse, our knowledge falters. Exotic stars, strange matter, gravastars, these are attempts to bridge that gap, to imagine what nature might do when pressed beyond our current laws. And so the story of collapse continues past what we can confirm. It is not only a story of what has been observed, but of what may yet be discovered. If quark stars exist, they would represent matter in its rawest form, stripped of its familiar structures. If gravastars exist, they would represent space-time itself, taking on new states. The universe may already harbor these objects, hidden in the shadows, waiting for us to build the instruments capable of finding them. The lesson is simple. Collapse is not finished. Beyond stars as we know them, beyond remnants we can observe, there may be stranger fates. Gravity is not bound by our imagination, and the cosmos is under no obligation to limit itself to what we expect. The boundaries of collapse are the boundaries of physics itself, and until we understand both gravity and quantum mechanics as one, those boundaries will remain open, inviting speculation, demanding humility. The struggle between pressure and gravity does not end at neutron stars or black holes. It continues in theory, where physicists ask how far matter can resist before surrendering entirely. Every remnant is a balance point. White dwarfs survive through electron degeneracy, neutron stars through neutron degeneracy, black holes through the absence of resistance altogether. But what if other forms of pressure exist, hidden within the layers of physics not yet revealed? At the heart of the question lies the strong nuclear force, the most powerful interaction known. It binds quarks inside neutrons and protons, locking them together with energy so immense that splitting them requires particle accelerators. In a collapsing star, gravity presses with equal determination. If neutrons break apart, their quarks may form a new state of matter. Quark pressure could emerge as a final resistance, building stars even denser than neutron stars, but not yet black holes. These hypothetical quark stars would be thresholds in themselves, markers of a universe where matter surrenders, layer by layer, each collapse revealing deeper structure. Beyond this lies speculation about even stranger supports. Could spacetime itself resist collapse in new ways? Ideas like gravastars and dark energy stars suggest that vacuum energy or exotic fields might provide balance. These objects would appear nearly identical to black holes from a distance, but their interiors would lack singularities, replacing them with stable energy cores. For now, they are conjectures, but they reflect a truth. When matter is pressed to its limits, imagination and physics must both stretch to meet it. The limits of collapse also invite us to ask about the very end of matter. If no pressure can resist gravity, collapse continues without bound, producing black holes. But quantum theory challenges this picture. Some calculations suggest that at extreme densities, quantum gravity effects could halt collapse, perhaps creating remnants smaller than neutron stars but larger than singularities. Such remnants might explain mysteries like dark matter or solve paradoxes about information loss. Observations drive these questions forward. Pulsars too compact for neutron matter hint at quark stars. Gravitational wave signals from collisions may reveal subtle differences between neutron stars and stranger objects. Future telescopes may detect deviations in black hole shadows that suggest horizons are not what we think. Each new instrument presses theory against reality, narrowing possibilities, testing the edges of collapse. The lesson is clear. Gravity always seeks to crush, but matter resists in layers we are still discovering. Electron pressure, neutron pressure, quark pressure, perhaps even space-time pressure itself. Each has its domain, each sets a boundary, but gravity waits, patient, relentless, testing each frontier in turn. The story of collapse beyond stars is the story of how deep matter can go before it ceases to exist as matter at all. Collapse beyond stars is a frontier of speculation, a realm where the known laws of physics, fray, and imagination must step in to fill the gaps. We know with certainty that white dwarfs, neutron stars, and black holes exist. We have measured them, mapped their radiation, even imaged their shadows. But beyond these proven remnants lies an unknown country, populated perhaps by quark stars, gravastars, or even stranger objects. Whether or not they are real, the fact that our theories allow for them is a sign of how much remains hidden in the depths of gravity. The search for such objects is not just curiosity, it is necessity. In their extreme states, collapsed remnants probe the very heart of physics, uniting the infinitely small with the infinitely large. A neutron star is a laboratory for nuclear forces under pressures no machine on Earth could create. A black hole is a test of relativity under conditions of extreme curvature. A quark star, if it exists, would show us matter stripped to its most fundamental form. A gravastar, if real, would reveal a new state of spacetime itself. These are not just objects of astronomy, they are experiments, natural tests of the universe's deepest laws. Modern astrophysics advances toward these frontiers with instruments more powerful than ever before. Gravitational wave observatories listen to the ripples of collisions, recording the signatures of mergers that may distinguish neutron stars from exotic stars. Space telescopes track X-rays and gamma rays, searching for anomalies that hint at matter stranger than neutrons. Radio arrays time pulsars with precision, looking for irregularities that betray new physics. Each observation sharpens the map of possibility, narrowing the window where speculation may one day become certainty. Even so, the unknown remains vast. Perhaps quark stars exist only briefly, transient way stations between neutron stars and black holes. Perhaps gravastars are illusions, theoretical artifacts with no place in nature. Or perhaps they are real, hidden across the galaxy, waiting to be recognized. The truth is not yet ours, but the pursuit itself drives progress. By seeking the strange, we refine our understanding of the ordinary. By searching for what might be, we learn more of what already island. What matters most is that collapse always leads us to deeper questions. It begins with the fall of matter under gravity's pull, but it ends with the fall of our own theories, collapsing under the weight of their incompleteness. The more we learn of stellar death, the more we are reminded of how much we do not yet know. That is the true legacy of collapse beyond stars. It humbles us, reminding us that the universe is not finished revealing itself. The story of gravity crushing stars does not stop at stars. It extends into the unknown, hinting that even black holes may not be the last word. Beyond the horizon of our understanding, new forms of matter and energy may exist, awaiting discovery. And whether they prove real or not, the pursuit of them ensures that the story continues, a narrative of exploration as relentless as gravity itself. In the next and final chapter, we will step back and see the story whole. We will trace collapse from white dwarfs to neutron stars, from black holes to hypernovas, from proven remnants to speculative frontiers. We will see how stellar death serves as the recycling engine of the cosmos, how every destruction is also a creation, and how collapse itself has made life and galaxies possible. When gravity crushes a star, it writes not only an ending but the beginning of everything we know. The story of collapse is the story of the universe written in fire and silence. It begins in the hearts of stars, in the eternal battle between gravity pulling inward and fusion pressing outward. It ends in remnants that shape galaxies and seed worlds. Along the way, collapse reveals the deepest truths of physics, testing the strength of matter and the fabric of space-time itself. To trace the legacy of collapse is to trace the history of existence, for without it, there would be no galaxies, no planets, no life. Every fate of a star is a chapter in this story. The smallest stars fade into white dwarfs, remnants supported by electron pressure, glowing for billions of years as they slowly cool. Their deaths may seem quiet, but when paired with companions, they can explode as Type 1, a supernovae, sending predictable flashes across the universe that have become tools to measure cosmic expansion. Even in silence, white dwarfs leave their mark, for their atoms enrich the interstellar medium. Their explosions illuminate the scale of the cosmos, and their existence reminds us that collapse has many paths. More massive stars find harsher ends. Their cores burn heavier elements until fusion can go no further, until iron accumulates and gravity seizes control. Collapse follows in seconds, crushing matter until even electrons and protons merge into neutrons. The result is a neutron star, a remnant so dense that a teaspoon of its matter outweighs mountains. These stars are not only remnants but lighthouses, their beams sweeping through the galaxy as pulsars, their collisions forging gold and platinum, their precision revealing ripples of space-time in the form of gravitational waves. Neutron stars show us collapse as transformation, where destruction becomes discovery. Above them loom black holes, the ultimate victory of gravity. When mass exceeds the threshold, no pressure can resist. Matter caves in, space-time curves, and an event horizon forms, a boundary from which nothing escapes. Black holes are not merely corpses of stars, they are engines of galaxies. Their accretion disks blaze with radiation, their jets pierce space for thousands of light years, their mergers send waves across the universe. They embody collapse in its purest form, where matter ceases to resist and gravity reigns unchained. Yet even in this silence, they shape creation, anchoring galaxies, sculpting structure, and driving evolution. And then there are the extremes, the pair instability supernovae that obliterate their stars entirely, leaving no remnant, and the hypernovae that channel their fury into gamma-ray bursts visible across the observable universe. These rare deaths show us that collapse has no single script. Sometimes it leaves behind remnants, sometimes it erases them, sometimes it unleashes energies that challenge our imagination. In each case, destruction is also creation, scattering elements, shaping galaxies, and rewriting the cosmos on grand scales. Together, these fates weave the fabric of the universe. White dwarfs, neutron stars, black holes, hypernovas, all of them are not just consequences of collapse, but instruments of cosmic renewal. The oxygen we breathe, the iron in our blood, the gold in our hands, the very structure of galaxies, all are legacies of stellar death. Collapse is not an end, but a cycle, the means by which the universe grows complex, diverse, and alive. The legacy of collapse is written into every corner of the cosmos. Stars live by burning hydrogen into helium, by building heavier elements, layer by layer, and then by scattering those elements back into space when fusion can no longer continue. Without this recycling, the universe would be a barren place, filled only with hydrogen and helium from its earliest moments. But collapse changes that emptiness into richness, seeding the raw materials for planets, oceans, and life. In this way, death becomes the architect of creation. Galaxies are not static collections of stars, they are ecosystems in motion, shaped by collapse as much as by birth. Supernovae sweep across them like storms, blowing bubbles in the interstellar medium, stirring gas clouds, and compressing them into nurseries for new stars. The shockwaves from stellar deaths can trigger waves of star formation, lighting up spiral arms with new generations. Black holes at galactic centers regulate this process, their outbursts quenching or igniting growth. Collapse is the heartbeat of galaxies, dictating when and where light will shine. The evidence surrounds us. The Milky Way's spiral arms glitter with young stars, born from clouds, enriched by countless ancient deaths. Nebulae glow with elements forged in explosions, their colors, the signatures of oxygen, nitrogen, and sulfur, flung into space. Even Earth itself carries the proof. The rocks beneath our feet are laced with atoms made in long-dead stars. The oceans carry oxygen born in stellar cores. Every breath we take binds us to the collapse of stars, for our lungs fill with atoms created billions of years before life began. Life would be impossible without this legacy. Carbon, the backbone of organic molecules, comes from red giants. Oxygen, essential for respiration, comes from massive stars. Iron, vital to the chemistry of blood, comes from supernovae. Even rare elements like iodine, molybdenum, and gold trace their origin to the violent deaths of stars. To exist is to carry within us the memory of collapse. We are not observers separate from this cycle. We are participants, its most complex expression. The recycling of collapse is also the reason the universe grows ever more diverse. The first stars, born from pure hydrogen and helium, could form only primitive planets, if any at all. But as generations lived and died, the interstellar medium grew richer. Each cycle added heavier elements. Each death expanded the palette. From this enrichment came rocky worlds, complex chemistry, and the possibility of biology. Without collapse, no planet would carry continents or oceans, no organism would carry DNA, no civilization would raise its eyes to wonder about the stars. Yet the legacy of collapse is not only material, it is also cosmic in scope. Black holes merge and send gravitational waves rippling across space-time, waves that carry information about the universe's most extreme events. Neutron stars collide and light up the cosmos in kilonovae, producing elements and revealing the physics of dense matter. Type 1, a supernovae, mark distances across billions of light-years, allowing us to measure the expansion of the cosmos. Stellar death has given us the tools to understand the universe itself. When we map galaxies, when we measure the speed of cosmic expansion, when we detect gravitational waves, we are listening to the echoes of collapse. The universe is not silent, it speaks through the deaths of stars. Every measurement, every discovery, every step forward in science has been guided by the legacy of endings that are also beginnings. Collapse is both the subject and the teacher, both the destroyer and the guide. The story of collapse is, in truth, the story of the universe becoming itself. Without the deaths of stars, galaxies would be pale structures, barren spirals of hydrogen and helium. Without collapse, planets would not exist, elements would not diversify, and life would not arise. Gravity's relentless victories, each marked by the extinguishing of a star, are the very reason the cosmos has texture, color, and meaning. Think of the pathways we have followed. Small stars end as white dwarfs, silent embers supported by electron pressure, glowing as they cool across billions of years. They remind us that even quiet deaths shape the universe, for their matter is returned to the interstellar medium, enriching the gas from which new stars form. When paired with companions, they ignite again in thermonuclear supernovae, standard candles that illuminate cosmic distances and reveal the accelerating expansion of space-time. Heavier stars find harsher fates. They collapse into neutron stars, city-sized remnants of incredible density, whose pulses echo across the galaxy as lighthouses of gravity and time. In their collisions, elements like gold and platinum are born, their brilliance lighting the night sky for weeks. They show us that collapse can create as much as it destroys, that endings can forge treasures to be held in human hands billions of years later. Above them loom black holes, where gravity's victory is absolute. The event horizon is the point of no return, the edge beyond which even light cannot escape. To us they appear silent, but their influence stretches across galaxies. Their accretion disks blaze, their jets pierce interstellar space, their mergers shake space-time itself. They are collapse in its most unrestrained form, yet they are also creators, anchoring galaxies and shaping the architecture of the universe. And beyond these known fates lie the extremes, pair instability supernovae, where stars annihilate themselves completely, scattering every atom into space, hypernovae, whose jets shine as gamma-ray bursts brighter than billions of galaxies. These are rare, but their echoes reach across the observable universe, reminding us that collapse can also be spectacle, a display of violence so fierce that it becomes beauty. Taken together, the deaths of stars are not accidents or afterthoughts. They are the engines of cosmic renewal. Every white dwarf, every neutron star, every black hole, every supernova contributes to the cycle that makes the universe rich and alive. Collapse is not simply destruction. It is transformation, the handing forward of matter and energy from one generation to the next. It is the mechanism by which galaxies breathe, the process by which planets form, the reason why life is possible at all. We who tell this story are also part of it. The atoms in our blood were born in stellar furnaces, scattered by explosions, gathered into clouds, and forged into Earth. We are the children of collapse, living proof that the universe's most violent acts can create the conditions for thought, memory, and wonder. When we look at the night sky, we are looking into our own history, for every star that shines is part of the cycle that made us possible. The legacy of collapse is not merely scientific, it is poetic, existential, profound. It tells us that endings are never only endings. It tells us that destruction can be creation, that silence can be power, that death can be the foundation of life. Collapse is gravity's triumph, but it is also the cosmos's gift, the process by which the universe evolves toward complexity. And so we arrive at the final truth. When gravity crushes a star, it is not only an ending, It is the beginning of everything we know. The galaxies above, the planets beneath our feet, the breath in our lungs, the thoughts in our minds, all of it is the legacy of collapse. In every ending lies a seed, and in every collapse lies a universe waiting to be born.